Okay, so this video is going to be on electricity. It's on Coulomb's law and circuits. I'm going to be real with you. This is not everything you could potentially see on the AP that has to do with electricity. We would need to spend probably way more than the length of this video to cover that. I will post the reading guides associated with the chapters in the book on electricity and circuits if you feel the need or decide to take the time to go through them in more detail. However, but due to time and due to the fact that a lot of what the AP is going to ask you is logic based, and I feel like if you have a firm background in the rest of it, which I feel like you should, then you'll be okay on these last two topics, electricity and circuits, and then waves and light, that we didn't cover in a whole lot of detail, that you'll still be okay. So where this actually came from is the 5 Steps to a 5 book. I literally took the chapter on electricity and circuits and made it into a reading guide. Dear Greg Jacobs, if you find this video, I don't know whether doing this was actually legal, but I have strongly upsold your book to my students, and I think you're a real great teacher, so please don't, sue me. Alright, so let me jump in here instead of being awkward. You will notice that I am now I'm letting you see my face while I record so that the awkwardness is physically present, because apparently that's what you guys enjoy most about these videos is the awkward. So, the summary of the entirety of electricity is that you have Coulomb's law, which talks about the force of one charged particle on another, and it's given by an equation. AP Physics 1 deals only with electrical forces that are acting between exactly two charges, which makes things a lot nicer. AP Physics 1 also requires an understanding of direct current circuits, including series resistors, parallel resistors, and combinations thereof. This will show you how to deal with circuits, including both conceptual descriptions and using calculations. Conceptual descriptions is for us perhaps more important. I believe in your ability to do the calculations, even if you've never seen the equation before, because there's literally a section on the formula sheet that says electricity, and you can be like, all right, I'm going to find one of these formulas that seems to fit. So let's talk about what kind of terms you're going to see when it comes to electricity. We have a series of definitions here. Electric charge. The variable for charge is uppercase. It's sometimes lowercase. The AP seems to use uppercase, so that's what I will do, is Q. I know there's no Q in charge. Listen, we have to stop expecting those things to make sense at this point. Electric charge exists due to excess or deficient electrons on an object. So if something has equal amounts of protons and electrons, then it's neutral. This is going to talk about it later, but I'll just briefly. And then if it has more electrons than protons or vice versa, it has electric charge. We've also talked about the fact that it would make the math involved a lot simpler if we had given our charges, our electrons and protons, opposite charges, but we didn't, and there's no going back now. Charge comes in two types, positive and negative. The unit for charge is the coulomb, and I can never spell it right. It is a guy's name, and we abbreviate that with an uppercase C, which at least that does make sense. 1 coulomb is a lot of charge, for the record, so if you're doing a problem that has real numbers, it'll often be a very small amount of coulombs, but luckily a lot of what the AP does are more conceptual rule of ones type questions. Electric current is the flow of charge per second. It's done with an uppercase I. I know that's also rotational inertia or moment of inertia. Fortunately, those two are never going to occur in the same problem. There's never going to be here's a circuit that's also rotating. No. So if you're dealing with electricity and you see an I, it's current. The units of current it's literally coulombs per second, but we gave that its own name, which is the ampere, which is often abbreviated as amps or just uppercase A. 1 ampere means 1 coulomb of charge per second. Resistance which is given by an uppercase R, is measured in ohms. That's not a Q. I'll fix this before I print y'all's copies. That's an uppercase omega. which should make sense, ohms omega, tells how difficult it is for charge to flow through a circuit element. It's literally resistance to current. Resistivity lowercase p, again, I know lowercase p is also momentum, but again, you're not going to see these two in the same problem, is a property of a material, which implies that the resistance would be of a, which implies what the resistance would be of a meter cubed bit of that material. I actually think this is supposed to be rho. I'll double check that before I print your copies. Rho is the Greek letter that's like a slightly squished P. Resistivity is not something that I super anticipate you being asked about, but I am not an AP reader or writer, and Greg Jacobs is, so what do I know? It doesn't seem as important to me as these other concepts. Voltage is another big one. Voltage is electric potential energy per coulomb of charge. So it's not energy, it's not measured in joules, but it's related heavily to energy. So we can think about it kind of like it's energy, but it's how much energy per individual charge you have, per coulomb of charge. Resistors are connected in series if they are connected in a single path, and they're connected in parallel, LLEL, if the path for current divides, then comes back together. All of this is going to make more sense once we work through the rest of the packet. The AP Physics 1 algebra-based exam requires you to learn two aspects of electricity. First, you must understand how charged objects apply forces to each other in isolation, as when a balloon sticks to a wall. Then you need to know about circuits in which gazillions of submicroscopic flowing charges produce effects that can be measured and observed. The pictures over here show a circuit. This is a circuit. This is a breadboard. I'll try to, oh, you can't see. I'll try to show you guys physical examples of these in class, and we'll talk about them a little. This is a breadboard that has two light bulbs hooked up to it with wires, in which the flow of charge causes the light bulb to light up. The meter positioned, this thingy, is here to read the voltage across the two bolts. You do need to know a little bit about how to use voltmeters and ammeters because they could come up on the experimental free response question. All right, let's go back and talk about electric charge in detail. All matter is made up of three types of particles: protons, neutrons, and electrons. Protons have an intrinsic property called positive charge. Again, this saying intrinsic and positive, it has an intrinsic property that electrons have a opposite intrinsic property. We decided that it would be best to talk about those in terms of positive and negative signs, not because they're actually in some way positive or negative, but because they are opposites, and that's an easy way to represent opposites. We really should have named them backwards. I don't know why I keep harping on that. I think it's just because it's a fun fact that I know, and that it's Benjamin Franklin's fault. We've already written this, but we're going to write it again so that you'll remember. The unit of charge is the coulomb, which is abbreviated C. One proton, this is important. I told you that a coulomb was a lot of charge. One proton has a charge of 1.6 times 10 to the negative 19th coulombs. Now that's a vaguely terrifying number, but there's two good things. One is one of the things that he talks about, that Greg Jacobs talks about further in this packet, is that you're probably not going to be asked to do a whole lot of math using this. It's going to be mostly conceptual. The other is that you don't have to memorize that number. It's literally on the formula sheet. Yay! So, most objects we encounter in our daily lives are electrically neutral. like couches, for instance, or trees, or bison. These objects contain as many positive charges as negative charges. In other words, they contain as many protons as electrons. When an object has more protons than electrons, it is described as positively charged, and when it has more electrons than protons, it is described as negatively charged. The reason that big objects like couches and trees and bison don't behave like charged particles is because they contain so many protons and electrons that a few extra aren't going to make a difference. So every atom in your couch is not electrically neutral. No, probably a bunch of them are negatively charged or positively charged, but there's so many overall that, like it says here, even though they might have a small electric charge, the charge would be much too small relative to the size of the object to detect. Tiny objects like atoms, however, more commonly carry measurable electric charge because they have so few electrons and protons that an extra electron makes a big difference. You can also have a very large charged object. When you walk across the carpeted floor in the winter, you pick up extra charges and become a charged object yourself until you touch a doorknob, at which point all excess charge in your body travels through your fingers into the doorknob, causing you to feel mild electric shock. So you lose or gain enough, I honestly can't remember which it is. I think it's that you gain extra electrons when you're like shuffling with on carpeted feet. You gain enough extra electrons that you actually have a measurable charge, despite the fact that you are a very large object. Electric charges follow a simple rule. Like charges repel, opposite charges attract. Two positively charged particles will try to get as far away from each other as possible, while a positively charged and a negatively charged particle will try to get as close as possible. Only two types of charge exist. If a question on the exam purports to give evidence of a third type of charge, reject that evidence. If a question suggests a type of charge that repels both positive and negative charges, reject that suggestion as silly. This is kind of important because they like questions like this. They're like, two students do an experiment and their results indicate that there's a new type of charge. Tell whether you agree with it. And you should immediately be like, no matter what evidence they give, you should be like, that's impossible. There's only two types of charge. And then you should look at their evidence and try to figure out what they've done wrong. So, Coulomb's law. Exactly how much do charged objects attract and repel? Coulomb's law gives us a number. Coulomb's law is on the formula sheet. Under electricity. It's this right here. And we're going to write that. It's an equation for the force exerted by one electric charge on another. And it says that the electric force is K Q1 Q2 over... what variable does he use? D squared. The AP uses an R here. Oh, you can't see. The AP uses an R for that D, but it's really not an important distinction there. So let's talk through those variables. The two Q's, and so actually I was wrong. Greg Jacobs uses uppercase Q, but the AP formula sheet specifically uses lowercase q. It really doesn't matter. If you see a Q, it's charge. The two Q's represent the amount of charge on each object. The D represents the distance between the two objects. The variable K is Coulomb's law constant. Remember that when we're talking about motion, K is the spring constant, which changes based on the spring. Don't get that confused. This is Coulomb's law constant, which is always the same number. It is given on the AP formula sheet. It's a hot mess. It's 9 times 10 to the 9th Newton meters squared per Coulomb squared. As with Newton's law of universal gravitation, which we did a worksheet on in class, you're probably not going to be asked to calculate much with Coulomb's law. You're not going to be asked to plug in tons of numbers to this equation, because that's just not what the AP is trying to test. However, questions will be qualitative and semi-quantitative. For example, if the amount of charge A is doubled, what happens to the force of... Okay, so I did the thing again where it cut me off and I didn't realize it, so I kept talking. So instead of trying to reprint this and rewrite it, I'm just going to walk you through what I did. So we were saying what happens to the force on charge A, the force of charge A on charge B if charge A doubles. Well, using the law of ones, K stays the same, one of the charges stays the same, one of the charges becomes a 2, the distance stays the same, you end up with an answer of 2. The way to interpret that is it's doubling. What happens if you double the distance? Well, in that case, K and both Q's are staying the same. Distance is doubling, distance is squared. This is another inverse squared law, which we talked about with gravitation. So it's 1/4, so the force is cut by 1/4. And that's all it spends on, all Greg Jacobs spends on Coulomb's law. Example problem number 4. Or practice problem number 4 at the end of this is related to this, but I trusted judgment that we don't need to spend a whole lot of time on it. Next, we have another conservation law. Much like energy and momentum, the total amount of charge in a system, or indeed in the universe itself, is always the same. Equal amounts of positive and negative charge can cancel out to make an object neutral, but those charges still exist on the object in the form of protons and electrons. Charge can be transferred from one object to another, for example, by touching 2 charged metal spheres together or shuffling your feet on the carpet, but the total amount of charge in the system, you and the carpet or the 2 metal spheres, stays the same. Conservation of charge is usually discussed in conjunction with circuits and Kirchhoff's junction rule, which is discussed below. So that's just, if you're ever presented with a situation where it looks like charge is being created or destroyed or changing, somehow it's not. Reject that. Circuits. A circuit is any wire path that allows charge to flow. So flow of charge is super important here. That's current. And a circuit is a path for current. Technically, a current is defined as the flow of charge. I just said that, jumped the gun a little, sorry. Under what conditions would charge flow? Charge would flow when a coulomb of charge has a potential energy that's higher at one position on the wire than the other. We call this difference in potential energy per coulomb voltage. And a battery's job is to provide this voltage that allows the current to flow. Current flows out of a battery from the positive boop, to the negative. I can never spell the word negative. It's an A. All right. Resistance versus resistivity. Resistance tells how difficult something is for a charge to flow through. Usually that something is a resistor or a light bulb, or is something that has a known and determinable resistance. Usually resistance of a wire connecting to the somethings is nothing, at least compared to the resistance of known things. The resistance of a wire of known dimensions is given by uppercase R equals rho L over A. And for the record, here, rho is resistivity. L would be the length of whatever you're talking about, and A would be the area. I don't really see, again, you being asked about this. They're going to ask about resistance, but not in terms of this equation. Instead, oh, well, this is continuing that conversation. Let me just be awkward at you. I was doing so well. So occasionally it is important to use this equation to know how the properties of a wire are going to affect its resistance. The longer the wire, if you look at this equation, the longer the wire is, the greater the resistance is going to be. The wider it is, the greater the area, the smaller the resistance is going to be. Imagine a pipe. The bigger the pipe is, the easier water can flow through it. Two wires with the same shapes can have different resistances if they are made of different materials. That different material is what goes into resistivity. Assuming the same shape, the wire with more resistance has greater resistivity, which is represented by rho. That is a rho. I looked it up. All right, so here is a circuit. The preceding diagram contains a battery and 3 identical 100 ohm resistors. So charge is flowing this way, and we have 3 different resistors. Questions about circuits will occasionally ask for calculations. Find the voltage across each resistor and the current through each resistor. More often, though, you're going to be asked qualitative questions, like which bulb or resistor takes the greatest current, or rank resistors from least to smallest voltage. So to be able to answer questions like that, we need 4 new facts. And when he says fact here, those are fact book facts again. Series resistors carry the same current, which is equal to the total current through the series combination. So when you're dealing with series is literally, if you had a circuit, I'm kind of sad this doesn't show it. I guess Greg Jacobs assumes you were taught this already. If you had a circuit that looks like this, I'm terrible at drawing resistors. This is like R1, R2, R3. There's only one path here for current to take. So all of this is in series. And they would all have the same current, and it would be equal to the total current through the battery. The voltage across series resistors is different for each resistors, but it adds up to the total voltage of the battery. So you can think of it almost as, when you're dealing with a series circuit, as if it's using up some of the battery's voltage. So this resistor is going to use some, this resistor is going to use some, this resistor is going to use some, and then the voltage used by each one will equal the voltage of the battery. Now, things work a little bit different in parallel. The voltage across parallel resistors is the same for each and equal to the total voltage across the parallel combination. Parallel is when current has a choice. Like here, it can choose to go this way, it can choose to go this way. For these, they're always going to use, there's going to be the same amount of voltage for each path. And they add up to what the voltage of this combined piece would be. There's supposed to be a fourth thing here, which I will make sure I add before I print your copies, which has to do with, you may notice we did series current, series voltage, then we did parallel voltage. We need parallel current. I can't even spell. The current through each path is different. And it adds up to the total. So you'll notice these are backwards. For series, the current is the same everywhere, voltage adds up. For parallel, voltage is the same everywhere, current adds up. The problem is that you're not going to see ones that are just series, or like just parallel would look like this. You'd have your battery. That would be just parallel, but you're not going to see those. You're going to see combinations. So then you have to do more complicated stuff. Tip from AP Physics Veteran. Most first-year physics students are more comfortable making calculations with circuit problems than with explaining effects in words. If you are confused by a qualitative circuit question, try answering with a calculation. Well, with a 150-volt battery, there's a calculation showing I get 1 amp of current in the circuit, but with a 75-volt battery, I only get 0.5 amps. Thus, cutting the battery's voltage in half also cuts the current in half. This is the same thing I've been telling you. If you super don't understand how to use the rule of ones, make up numbers, see how it affects your answers, and then use that to get further, to answer the question. To go back, you can't just put your numbers that you made up as the answer, but if you look at how your numbers changed, you can get your answer. Now, here's the big chunk of this packet. When you see a circuit, regardless of what questions are asked, it's worth making a VIR chart listing the voltage, current, and resistance for each resistor. Then use the 4 facts about Ohm's law, and the equation V equals IR can be used to find the missing values of any point on the chart. You're going to need a separate piece of paper for this part, and we're going to walk through how we would make a VIR chart and find all the possible information about this circuit. Then if you saw a question on the test that asked you anything about this circuit, you'd be like, all right, I know I can make a chart for that and end up getting the answer. All right, so again, I said you were going to need a separate sheet of paper, and you're going to set up what they call a VIR chart. The way you're going to do that, and you may want to pause to make yours, is you're going to have your number of resistors down the side. In this case, if we go back to our picture, we have 3 resistors. 3 resistors and then our totals, and then across the top you'll have V for voltage, I for current, R for resistance. You want them in this order, which we'll talk about in a minute. If you didn't have 3 resistors, if you only had 2, you'd only have 2 rows here. If you had 4, you'd have 4 rows here, so on and so forth. Then the first thing you do after sketching your chart, please actually make this chart because these charts are so important for current circuit problems. After you make your chart, you know you fill in what you know. So we know that all 3 of our resistors are 100 ohms. We're not given a voltage, so we're going to make one up. We're going to do that V total is 100 volts. Why can you just make one up? Because if you're being asked something qualitative, if you're asked to rank the resistors, it doesn't matter how much current you calculate as long as it just matters which one gets the bigger current. So any reasonable value will do for making up a voltage in terms of qualitative questions. Next, we're going to simplify our circuit, collapsing sets of parallel and series resistors down into their equivalent resistors, which is a fancy way of saying we're going to think about the circuit in simpler terms. So, the equivalent resistance through a series circuit is the sum of all the individual resistors. The equivalent resistance of parallel resistors is less than any of the individual resistors. We're going to skip around a little because I don't particularly like the order he did this part in. I might fix it on your sheet. The equation, if you need to figure out the equivalent resistance for parallel resistance, is 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 plus ... because you could have, however many resistors. The AP writes this in a way that I'm unhappy about. I'm unhappy about a lot of things. The AP writes that 1 over resistance parallel is equal to the sum of 1 over Ri, and you're summing with I. Is that the same thing? Yes. Is it way more confusing? Yes. And so this is parallel, LLEL. For series, it's actually much simpler because it's just the sum, which the AP chooses to write like that. I would write it as just REQ through series is R1 plus R2 plus ... however many you have. So, here's the deal. This equation is kind of unfortunate and scary because there's fractions involved, and then you actually have to add the fractions and take the reciprocal since you're looking for this number. However, when two identical resistors are connected in parallel, which is what we have here, we have 100 plus 100, the equivalent resistance is going to be half of either resistor. So here, the equivalent resistance of R2 and 3, and feel free to do the math to check that this works out, I promise that it does. The equivalent resistance of R2 and 3 is just 50 ohms. This doesn't really go anywhere on our VIR chart. You could kind of write it in here that like this is 50 ohms combined. That's not super useful on its own, but it's going to be useful in terms of getting us other things. We can now redraw the whole circuit to look like this, where we still have R1, but now this is what I'm going to call R2, 3. It's the equivalent resistance from 2 and 3. Since these two are now in series, there's only one path to get from one to the other, then you can just add them. So our R total here is 100 plus 50, or 150 ohms. Excellent. That is something we can add to our VIR chart. We can now fill in here 150 ohms. Now, this is where people make mistakes. The VIR chart is not a magic square. It's simply a tool for organizing your calculations. You cannot just add up the values in a column. You're going to be tempted to, because sometimes you can, but not always. And when you're dealing with what's called a combination circuit that has series and parallel, you can't. It's just not a thing. Like, none of them are going to add up neatly. If you're dealing with just series or just parallel, then like at least one of your columns is going to add up neatly. So again, I like the term magic square. Like, you can't just add numbers. Don't get tempted to do that. All right. Oh, okay. So what you're looking for in the VIR chart, though, is anytime you have two of the three in a row, you can find the last one by Ohm's law. Ohm's law is the equation voltage equals current times resistance. This is like maybe the most important equation in all of electricity, V equals IR. That's the reason that we wrote our things in the order we did in our VIR chart, because then you can literally think of it as V equals I times R. Here we know V and we know R. It can only be used across a single row, for the record, so no like skipping around or anything crazy. So we can fill in the total current, because we know that 100 is something times 150. So working backwards, we have 100 equals I times 150. I equals 100 over 150. So now we can fill in that I total, that's not the pen I want to be using. I was afraid the light green wouldn't show up well. I total is 0.67 amps. All right. Now what? We can't use Ohm's law because we don't have any rows missing just one, because these are all missing two things. However, we can go back to our 4 key facts. Resistor 1 is in what with the battery? So let's look at our original diagram. How many paths the way to think about this, does the voltage from the battery have any choice but to go through R1? No. So these two are in series. So resistor 1 is in series with the battery, since the current flowing through the resistor. And then if we look at our four effects, since the current flowing through a series resistor is equal to the total current, I just bumped my camera, R1 must take the same current flowing through the battery. Aha! So now we can put 0.67 amps as the current through R1, 0.67 amps, which then allows us to easily get the voltage here, because V is I times R. So this is 67 volts. Now to figure out R2 and R3. Look at their 50 ohm equivalent resistor in the redrawn diagram. So now we're looking at, what did I just do with that picture? Here, we're looking at this picture. And it says, how is this connected with this? Well, after the current's gone through here, does it have a choice but to go through the combined resistor? No. So it's in series with the 100 ohm resistor. Note that R2 and R3 are not in series with it. It does have a choice, but their combined resistance is in series, and we can treat them the same. Oh, you can't even see the diagram here. Doesn't have a choice, so they're in series with each other. Therefore, that 50 ohm equivalent resistor must add its voltage to get the total voltage of 100 volts, and the voltage across the 50 ohm resistor is, okay, I messed that up, sorry. So what it's saying is that when you treat it as if you only have two, we know that V total is 100, because that's the number we made up. We just found that V1, or the voltage through resistor 1, is 67. And if these two are connected in series, from our four facts, the voltage through series resistors is different, but adds up to the total. The total is 100. We already have 67. So each of these, so the 51 must add its voltage to the 67 and combine to 100, which means that each one must be, that this 50 ohm must be 33 volts. Now look at the facts again. Parallel resistors take the same voltage across each one. So that means that if we know that their equivalent resistance is going to take 33 volts, then each one of them takes 33 volts. 33. Now we can use V equals IR to find out what I is. Notice that we didn't divide it up. The equivalent resistance took 33, so each one took 33. Now, the currents here are going to end up being the same because the resistors are the same. So we have 33, 33 equals I times 100, so I is 0.33 amps and 0.33 amps. So now we have a completely filled in V equals IR chart, which is beautiful. This chart can be used to answer any qualitative question. You need to give more explanation than just look at the chart. The chart is going to ensure that you get the right answer and that you have a clue of how to approach the qualitative question. For example, the exam might ask the following. Rank the voltage across each resistor from largest to smallest. It would be R1 is greater than R2, which is equal to R3. Justify that with a verbal description. you would say what you just did. Look at the simplification of the circuit to two series resistors. The voltage across the two series resistors must add to the voltage of the battery, but the current through them must be the same. By V equals IR, the bigger resistor is going to take the larger voltage. This is R1. Then R2 and R3 take equal voltage because they are in parallel with one another. So you're using things from the fact book and backing them up with the ideas from your table.